All right, so we have this interesting exercise, which is interesting in the sense that it's we're proving something that you are sort of told when you first learn calculus, which is that the integral of a definite integral is the same as the area under a curve. And here we're actually proving it mathematically, which is really neat when we get to actually prove things that you were previously just told blindly and not given a rigorous explanation for. The downside here is that there's something missing from this problem statement. So let f be as above and assume f is bounded by m. Because the issue is that we can't find the area of AF. Basically the way that you find the area of AF is by using Fubini's theorem. But Fubini's theorem only applies to computing integrals on closed rectangles. And these closed rectangles have to be bounded. So this doesn't work for unbounded intervals, which is an important distinction because this statement, in terms of measure theory, it ends up, I haven't done it, but I mean, I'm almost positive that this does work for integrable functions which are unbounded. So like just think of, for example, the function 1 over x squared on the interval 0 to 1. You can probably prove the same exact thing here for that function, but you won't be able to do it using Jordan measurable sets. And this is something like I sort of checked. I looked online to see if I could find other solutions to this exercise, and none of them mentioned boundedness of f at all. And so, I mean, I do wonder if there is a way to, like, maybe if you choose some large number m and prove the statement for the function g, which is the minimum of f and m, and maybe you prove the statement for g, and then you take the limit as m goes to infinity. But I'm not sure if you can make that rigorous. And I don't think that that's what they intended you to do here. What I think they wanted you to do is just simply assume that f is a bounded function. Which is also important because, like, there's actually another exercise in the previous section. Maybe I've done it by the time this problem, or by the time you're watching this, maybe I've solved that problem already. But there's a problem that I've skipped over in the previous section where you're basically allowing a function f to be equal to an indicator function on a set, but you allow it to vary on a set of measure 0. We don't know what values it takes on that set of measure 0. It could be unbounded on that set of measure 0. And all the techniques that we know from the previous section only apply to bounded functions. So none of those techniques from the previous section should be able to apply to this problem, which was stated in the previous section. And so for that reason, I feel like this detail about functions being unbounded is something that's seems to be like chronically not addressed in the problem statements of this textbook. But I mean, to be fair, it's really not that big of a deal. I mean, it is a big deal in the sense that it technically needs to be mentioned, but I mean, the spirit of the problem is sort of what I'm going to show now. And the thing about f needing to be bounded is just more of a technicality. But anyways, So f is above, assume f is bounded by m and non-negative. Let's see here. And so we have AF is this set. So basically, like if you have this function and it looks like this, maybe, let's make it look like that. And this is the x-axis and y-axis, x and y, then this set looks like this, basically. So you've got the left-hand side, the right-hand side, the bottom, and the top. Okay. So, what is the boundary of AF? And this, we can sort of just look at the set and see what it should be. Well, you've got this vertical line. We have 4 segments. We have this vertical line on the left, a vertical line on the right, a flat line on the bottom, and then you've got the actual graph of the function on the top. So let's see here. We'll call those 4 sets C1, C2, C3, C4. And so C1, we're going to let that be the left vertical line. So the x value is, this is a collection of points where the x value is a and the y value ranges from 0 to f of a. So it's a cross the closed interval from 0 to f of a. And then C2, so that's just going to be, let's go with the right vertical line. So that's going to be b, and then we'll have all values from 0 to f of b. And next we've got the thing on the bottom, so all the x values will range from a to b, and the y value is always 0, so it's this. And then the last thing, this is going to consist of all ordered pairs. We've got x and then f of x. And this is where x ranges over all values between a and b. C1, C2, and C3 have measure 0. And why is that? That's because, let's see here, so C1 is just this A cross 0 to FA, and you can basically cover it by a rectangle, which is a vertical rectangle, which is as thin as you want. So let's say the y values will still go from 0 to f of a, and the x values will go from like a minus epsilon to a plus epsilon. And then the total area would be, let's see here, 2 epsilon times f of a. And so if you chose epsilon, so if you're given an epsilon and you choose, instead of epsilon as that length there, you choose it to be like epsilon over 2 times f of a, then you get the area of this rectangle to be less than epsilon. And so, yeah. And then you can do that for C2 as well. You just take a really, you find a rectangle that is tall but really thin. And then for C3, you cover it with a rectangle which is short but wide enough to cover the interval from A to B. And then C4, which is sometimes called the graph of f, has measure 0 since given epsilon greater than 0, there is a partition P, and this is a partition of the domain AB such that the upper sum minus the lower sum is less than epsilon. And if we let Q be a collection of sets, so we're going to take I cross, so let's see here. P is a partition of A, B, so we're going to consider intervals in this partition P. So it's going to be you take this interval and you cross it with the infimum over this interval of F, and then the max over the interval of F. You do this over all I intervals I in the partition P. Then Q covers the graph of F4, the graph of F, which is C4. And why does it cover this? It covers it because here, why does it cover the graph? It's because what we're doing is if you consider the interval I, F will take on various values in this interval I. And these values will, by definition, lie between the infimum over F, the infimum over I of F, and the supremum over I of F. And these supremum and infimum values, these are precisely the lowercase MIF and the uppercase MIF, which are the upper and lower bounds of this, the corresponding element in Q, this I cross MIF, MIF. So every point in the graph can be covered by an element of Q. So Q covers the graph of F, and the total volume of the elements of Q is, well, you take the sum over all let's call it rectangle R in Q, the volume of R. But every rectangle R in Q is of the form I cross lowercase MIF, uppercase MIF. So it's going to be the sum over all I in P of the volume of I cross MIF, MIF. And now if we write out, one way to write out this volume is you can take, well, you can find it's just length times height. And so, let's see here, the height is uppercase MIF minus lowercase MIF. So it's uppercase MIF minus lowercase MIF times the length of I, which I will just denote by the volume of I. And maybe you can see where I'm going this. So this is, we can break this up into two things. So this sum minus this sum. And now maybe you can recognize this. This is precisely the upper sum minus the lower sum. And this we know to be less than epsilon. So maybe I went into more detail there than I needed to, but it's nice to show how this this partition of the interval gives you exactly what you need for this problem. All right, so so the boundary of AF has measure 0 because it's a union of countably many, in fact finitely many, in fact 4 sets of measure 0. So it itself has measure 0. So the measure of this boundary is 0, which means that AF is Jordan measurable. All right. So then the indicator function on AF is integrable. This is from the previous section. And yeah, this, yeah, so let's see here. Is this one of the things that requires it to be bounded? Yeah, I think this requires AF to be a subset of a rectangle, and thus it can't be unbounded. Yeah, so there we go. Now that because F is bounded, AF is bounded, and so this set is this function is integrable, the indicator function of the set. Okay, and so we all right. So now for a fixed x, we're going to let gxy be the indicator function of AF at xy, which is, well, the indicator function. So basically, x is fixed, and so if x is fixed, then if we look at the definition of AF, the y value for a fixed x, if you have a point xy that's in AF and x is given, the y value has to lie between 0 and f of x. So this indicator function here that tests whether the point xy is in AF, well, the x is fixed, and so for y, we need to test if y belongs to the closed interval 0 to f of x. All right, so we need that because that's going to be necessary for the integral. Because then, if we try to compute the area of AF, then this is going to be the integral, and we integrate over the domain, which is a to b cross 0 to m, which again, we need this closed interval here. And we're integrating chi AF. Oh man, I should have looked back to see what they put at the end of the integral here. I'm just going to leave it blank. But anyway, so this is going to be the integral over the x values, integral of from 0 to m of gxy dy dx. And so this is going to be the integral from a to b. And then if we're integrating this indicator function on 0 to f of x from 0 to m, basically this is going to be 1 if and only if x is between 0 and f of x. So this is just going to be the integral from 0 to f of x of the function 1 dy dx. And so then this is obviously going to be, well, you're just, if you want to do it calculus-wise, you take the antiderivative of 1, which is y, then evaluate that at f of x, which is f of x, and you subtract it, y evaluate at 0, which is 0, so you just get f of x. So this is the integral from a to b of f of x dx. And that is exactly what we were trying to prove. So, yeah, there was that thing that we needed to include there about the function needing to be bounded, but otherwise this proves that fact that we learned very early on in calculus, that a definite integral is equal to the area under the curve, which here is defined as the area of AF, and that is cool AF.